Thank you. Let us discuss the development of radar using software-defined radio hardware. And actually, even if you're not interested in radar systems, the outline of this presentation will be to show how we can try to benefit from various frameworks. GNU Radio for collecting data. GNU Radio Companion is a Python generator, so we might update the Python code and all this to process the data using the free open source MATLAB compatible GNU Octaves. So that's the outline of what I would like to show, is how to use the best of all these frameworks to efficiently process radio frequency signals. I'm presenting Jean-Michel Friedt, and this work was prompted by my colleague Weike Feng. So why are we doing this? Well, under these lockdown conditions, as we were watching from our balcony, opposite of a street, we saw this house, and we were wondering how far is this house. And we wanted to assess the statement from the French Geographic Institute stating that the distance from my balcony to the house is about 48 meters. So can we check using a radar system the distance between my balcony and this house opposite of a street? And actually, because we're under lockdown conditions, we're not allowed to go to the lab and collect hardware, so we need to try to benefit from whatever hardware we have available. So what do I have at home? I have some TV antennas, so that's TV UHF antennas, 400 to 700 megahertz, more or less. I have a PlutoSDR, software-defined radio from Analog Device. I have an Ettus Research B210, and various passive hardware, splitter, coupler, attenuators. So can we make a software-defined radio-based radar system, so radio frequency detection and ranging system, for measuring the distance to this house, which is about 48 meters? So the most basic approach would be to say that's easy enough. You have a B210. The B210 is a transceiver, so you might just emit using the transmitter of a B210, receive using the other antenna, and you have your radar. Well, the issue here is that a range of a radar is limited by the isolation between transmitter and receiver. Why is it? Because the ratio of received power to emitted power, if you extend Friis equation to the radar system, decreases as the fourth power of distance, if you assume that your target is a point-like target. And this means that you will only recover a minute amount of power, and if your transmitter to receiver coupled energy is too strong, it will hide whatever information has been returned by the target. So we need to have a good isolation, and although Analog Device will not document the isolation of the AD9361 on the B210, you will find on various forums and websites 60 to 70 dB. My measurements on the B210 are closer to 50 dB. So this is going to be a limiting factor in the range at which the radar can work. The other issue is that the AD9361 on the B210 uses two different local oscillators for transmitting and receiving. Actually, if you look on the receiver, the leaked power from the transmitter, you will see a slow drift of a local oscillator, and that's the local oscillator different between transmitter and receiver. So if we had different hardware like the Lime SDR, which uses the same transmitter and receiver local oscillator, such an issue would not raise. And if you have more fancy hardware like the evaluation board from Analog Device, you have a debug mode that allows for locking transmitter and receiver, but to the best of my knowledge, such a functionality is not available with the B210. So we need a way of transmitting a signal and measuring whatever is transmitted on the receiver side. So this brings us to the architecture that we selected. The PlutoSDR is a source, is transmitting a signal, so in this case a continuous wave, and the continuous wave we don't want to interfere with communication, so we send a minute amount of power, that's minus 30 dBm, that's a microwatt. Also because we don't want to damage the radio frequency front end of the B210, which is used on the one hand to collect whatever echo are reflected by targets, and we want to measure the transmitted signal, so we have a coupler, 10 dB coupler, we attenuate further to make sure we don't damage the front end, and this minus 60 dBm input signal is collected by the reference channel. So we use a B210 as a dual channel receiver, on the one hand measuring whatever is transmitted, on the other hand receiving echoes. So this is what it looks like. The B210 is collecting the two data from the two channels as a constant source is feeding the PlutoSDR, and these signals will be processed for compensating any offset between the PlutoSDR local oscillator and the B210, because of course these two local oscillators are not the same. How does it work? Well, if we measure whatever is being transmitted by the PlutoSDR, then we can assess on the reference channel the difference of the frequency between the local oscillator of the Pluto and the B210, that's this channel here. And because we know this difference on the signal that is received here, we can compensate by using the complex conjugate multiply, that's this block here. And by doing this, we cancel this frequency difference, and we're only left with, for example, if the target is moving, the Doppler shift between the transmitted and received signal. So what does this Doppler shift amount to? Well, if you take the example of a moving car, and you have to remember that in the case of a radar system, the Doppler shift is twice the local oscillator times the target velocity divided by the speed of light. That's because the electromagnetic wave goes towards the target and is reflected back. For a car driving at 15 meters per second, that's about 55 kilometers per hour, will exhibit a Doppler shift of about 60 hertz at 600 megahertz, which is about the center frequency of our antennas. So if we do this kind of processing, so using the two channels of B210 as it is fed with a continuous wave of a PlutoSDR and with a complex conjugate, we need to significantly decimate the signal to assess this kind of low frequency offset. So as cars are driving in front of a house, we have cars coming towards us, positive Dopplers, cars leaving away from us, negative Doppler. And despite the frequency difference, this is the wideband observation of the local oscillator leakage of B210, that's your frequency offset of the PlutoSDR. Despite these two local oscillators being slightly offset, because we compensate for this offset, we see here on the complex conjugate multiplication frequency output, the spectrum going from about minus 77 to plus 71 hertz, so that's well within the calculation we just did. And this spectrum was just grabbed as a bus was driving in front of a house. A bus is a huge radar cross-section, and you see here the bus at around 36 hertz. 36 hertz, if you convert this Doppler shift into a speed, is about 9 meters per second or 32 kilometers per hour, which is very reasonable for a bus driving on the street. So, okay, we have made a radar that works. It's a continuous wave radar, but we don't want to measure the speed of a house. We want to measure the range of a house, and the range is the velocity of light, 300 meters per microsecond, divided by twice the bandwidth. And the bandwidth of a continuous wave radar is basically 0, so we have no range resolution. So now the question is, how can we, from this setup, improve the range resolution by spreading the spectrum? How can we increase the bandwidth? So we do this by various means. The usual way is to use a chirp, so a frequency swept source, whether linear sweep, whether hyperbolic sweep. Martin Brown's PhD is about sum of orthogonal frequencies, so OFDM radar. We selected here an approach that I like, which is called noise radar. Noise radar is actually what you see in GPS with code division multiple access, using the pseudo-random phase spreading of a carrier transmitted by the GPS. So what we're going to do is actually, instead of sending a continuous wave using the PlutoSDR, we're going to send a pseudo-random noise sequence. And because this noise sequence, by definition, spreads over the whole spectrum, well, we know what this sequence is because we collect it on the reference channel. Then by looking at the reflected signal, if we correlate these two channels, we can find the time of flight on the dual channel receiver. So this has been very well known since 1957. The oldest reference that we found already states that this is a well-known technique. So let's see how we can implement this using a software-defined radio framework. So first of all, we would like to check whether we can spread the spectrum. So how do we spread the spectrum? The PlutoSDR now is not emitting a continuous stream, a continuous wave as was done before, but now we need to feed the PlutoSDR with a white noise. How do we create a white noise? We don't want to change power, so we have a constant power source here. So magnitude is kept at a unit value, but we want to change the phase, and the phase is actually the output of a noise source. This random noise source is an integer output. This integer is converted to a float. We remove the DC offset, and we convert this to an angle by multiplying by pi. So we have a pseudo-random sequence on the phase, constant magnitude. This stream of IQ feeds the PlutoSDR. Here we just want to characterize the spectrum, so we feed the B210 output to a frequency sink, one channel. And what you see here is the noise floor of the B210 is in blue. And if we accumulate in green here the spectrum, we see a nice flat spectrum, which is a characteristic of a white noise. So indeed, this approach is working. We do have a flat noise over the whole spectrum. Now the spectrum is limited by the communication speed between the laptop and the PlutoSDR, and we saw that we could actually transmit up to 2.7 megahertz. Above this, we had discontinuous spectra, the spectrum was dropping. So 2.7 megahertz is the maximum bandwidth that we can use for spreading the spectrum using this spread spectrum approach. So this is the complete setup, how we do the measurement. We have our pseudo-random source creating the phase modulation at constant magnitude feeds the PlutoSDR, and the two channels of the PlutoSDR will be the two channels of B210, one connected to the reference channel, the other connected to the antenna, will be analyzed. Now this analysis could be done on GNU Radio, but we see that for various reasons we would like to change framework, and we believe that most efficiently this analysis will be done in the MATLAB compatible GNU Radio software. So we would like to stream the data from the B210 to GNU Radio and to GNU Octave, and this will be done using the 0MQ framework. So what we do is we create chunks of data, we try to lower a little bit the bit data rate by taking 1 in n chunks of data, and we stream this to a 0MQ publish sync, which is pretty much like UDP, meaning if someone is listening, they collect the data. If no one is listening, the data are just streamed continuously and lost. Now 2.7 megahertz is only 56 meter range resolution, and 56 meter range resolution for measuring a house which is 50 meters away is not very good. So how can we further extend the bandwidth? Well, the obvious solution is to sweep the local oscillator. No one said you needed to collect the full bandwidth in one measurement. You can do measurements one after the other, which is your classical vector network analyzer implementation of a radar. And so we would like to give orders to the local oscillator to sweep both the B210 and the PlutoSDR local oscillators. I don't know how to do this from GNU Radio, and furthermore, I don't know how to tell GNU Radio to only analyze the data as the local oscillator are stable and not to analyze the data when the local oscillator are reprogrammed. So this is why we use these multiple frameworks. We're going to use Octave for processing, Python for programming the local oscillators, and the Python code has been generated from the GNU Radio companion. So this is how it looks like. On the Octave side, you have here the 0MQ. I would like to collect data only when the local oscillators are stable. So I open the socket when I have a new frequency that I want to measure. I connect here on the local host. I set as a subscribe, so that's a UDP-like socket. I collect how many data I want. These are 8-bit integers. I analyze these 8-bit integers as single resolution complex floating point values. I store my reference and measurements, and I continue after closing the socket to make sure I synchronize. This is not very elegant, opening and closing these sockets, but we measured it only takes about 130 microseconds, so it will not impact significantly on the measurement time. Now, this allows us to collect the data streamed using 0MQ on Octave, but the question is, how can we change the local oscillators? And if we analyze the Python code generated by GNU Radio Companion, you see here this callback function setf, and this setf function sets the local oscillator of the PlutoSDR and the USRP sources. So all we need to do is to address this callback function of setting the frequency under control of Octave, and this will be done nicely using a TCP server running on the Python code. So how is it implemented? Well, because GNU Radio is already blocking the main loop of the top block, we cannot loop our server in this function, so we need to create an additional thread. This thread will run the server, so we connect to the socket, which is a TCP connection. We listen for incoming connections, and when we have a connection, we analyze the messages that are transmitted on Octave. We also create the client socket, again a TCP socket, and we're going to send orders. So for example, before sweeping the frequency, we set to a startup frequency, and whenever we want to do a new measurement, we send that order to increment the frequency of above local oscillators. We increment the local oscillator frequency, and when we're happy with the new frequency, we call the callback function for setting the two frequencies. And by doing this, we can sweep over the whole frequency range and extend the bandwidth, so increase the range resolution. So this is where I mentioned that each framework will be used at best of its capability. So this is the actual implementation. You have the PlutoSDR generating this local oscillator, which is spread by the pseudo-random sequence. This is transmitted. We couple to measure the same sequence on the reference channel, and we have a measurement channel. Now you might see here that whenever we change frequency, we have to wait for 1 second, and we thought initially that this 1 second delay was due to the B210 stabilization time of UHD library. And actually I was told on the GNU Radio mailing list that some previous analysis hints that the local oscillator of the B210 can be swept much faster than 1 second. So the culprit is the PlutoSDR. We'll come back later to the issue of 1 second, but basically we have to wait for 1 second whenever we change local oscillator, and this will be the limiting factor in the speed at which we can observe targets. So here is an example of what happens. You collect the data in each frequency range, so 2.7 megahertz frequency range. You move by 1 megahertz. Here I just took a few spectra to make the chart clearer. And if you correlate the data collected in each one of these frequency range, you have poor range resolution. Well, nevertheless, you see that the correlation is negative is null at negative time. You see that it's asymmetric with some energy return at positive time, which is good for causality. And if we analyze all these spectra, one concatenated with the other, you see that now the correlation has a nice range resolution. Now, how come that this monotonous function can create this nice range resolution? Remember, these are all complex values, they have a phase, and when you add all these spectra, you have destructive interference between these echoes that will increase the range resolution. So if we collect all these spectra over 50 megahertz range, we have a 3 meter range resolution, but it takes about a minute to sweep the 50 megahertz range by 1 megahertz step. If we sweep 150 megahertz, we have 1 meter range resolution, and we're actually limited by the antenna bandwidth and the duration it takes for sweeping the whole range. But instead, you see that we can increase the range resolution by sweeping the local oscillator. So we do this over a whole frequency range, and by concatenating the spectra is like oversampling. So we take each one of the spectrum, we take the Fourier transform, concatenate all these spectra, and you remember that the correlation is calculated as the product of a Fourier transform of a reference times the complex conjugate of the Fourier transform of a measurement. And then by taking the inverse Fourier transform, we come back to the time domain. So we collect all this data for the reference, we collect all these spectra for the measurements, do the product of the two spectra, inverse Fourier transform, and in the time domain, here is a 50 megahertz bandwidth. We see an echo. This arrow tells you where the 50 meter target should be located, and 150 megahertz, you have here a sharper peak also located at the right range. So if you analyze by converting this time delay into a range by multiplying with a speed of light, 300 meters per microsecond, you have one echo at 250 nanoseconds, 350 nanoseconds, 360 nanoseconds, and 400 nanoseconds. If you put this on a map, this is the balcony. You have a first echo, which we analyze as being due to a car here. Then we have the front wall of a house. We have an echo that would be at the distance of the roof of a house, and an echo that is attributed to a tree here located next to the house. So we have two artifacts here. We know it's artifact because they also appear on the negative time domain, and these 1 microsecond artifacts are due to the 1 megahertz steps used to sweep the frequency. So we have a rather consistent image of the surrounding of a radar. Now you see here that the echo attributed to the chimney on top of a roof here is about the same amplitude as the echo due to the huge wall. Does it make sense? So the radar cross-section analysis here is driven by Franck Daou from UT Ville d'Avray, And how do you analyze this radar cross section? Well, you see here that the house is not facing the monostatic radar, but is at an angle. This angle can be derived by analyzing the ratio of these two walls, and by looking at the ratio of these two distances, we see that the angle is about 7 degrees. Now, this flat wall at an angle of 7 degrees will reflect the energy away from the receiving antenna. This is the basic principle of stealth planes and ships, with all these big flat areas that reflect incoming energy away from the receiver. And what you see here is that actually, because this wall is not infinite but it's finite dimension, you have a sine of x over x function, which at 7 degrees only returns a small fraction of the incoming energy, as opposed to the chimney here, which is about the same width as the wavelength of the incoming signal, and this chimney will scatter energy very well towards the receiver. So this tells us that this huge wall actually is going to send back the same amount of power as the small chimney, because not only is the wall reflecting away from the receiver, but furthermore it's made of dielectric, low permittivity dielectric, which only reflects a fraction of the incoming energy. So it makes sense that actually the chimney here returns the same amount of power as the wall here. So now we mentioned that we needed to wait for a second, and actually the issue that was documented by Travis Collins on the Analog Device website is that whenever we change the frequency, all the parameters of the PlutoSDR are changed, and one of them is requiring 1 second stabilization time. So if you read here on this GRIIO fork that was written by Travis Collins, there is a new single parameter option that allows you to only change the local oscillator frequency. And indeed, if you port this update of GRIIO to the 3.8 version of New Radio, now we have a stabilization time that is well within a few milliseconds. So by sweeping the frequency with such a high speed, by only tuning the local oscillator and not all the parameters of a PlutoSDR, now we can run about 100 averages, and it only takes the time needed to transfer the data from, to collect the data from the radio frequency stream to the PC to calculate the time it takes to do such a measurement. So if we collect 140,000 samples, which is the duration needed to get a fine correlation with a good signal-to-noise ratio at a rate of 2.7 megasample per second, you see that it takes about 50 milliseconds per frequency as opposed to 1 second previously. And this means that now sweeping 50 megahertz only takes 2.5 seconds instead of 1 minute. So now we can make averages by taking multiple measurements, and you see here the signal-to-noise ratio improvement by averaging 100 averages. The offset was included on purpose to make the chart clearer. So we now have a fast sweep with all these echoes that are attributed to the house, to the chimney, to the tree, and to the car with a very nice signal-to-noise ratio. So as a conclusion, we've implemented a software-defined radio implementation of a radar system. We try to separate the function and delegate the various frameworks, the function to the various frameworks at best. So using New Radio for data collection, Python for controlling all the hardware, and Octave for processing the data. Now, it could be possible to replace, here we use a B210, which is a rather expensive hardware. We could replace it with synchronous DVB-T dongles. We've done this already. So here you have these TV dongles, and many authors have shown that you could synchronize the two channels by feeding them with the same clock. I would advise using a differential clock feeding approach, but this works well. So you could replace the expensive hardware with some low-cost hardware, and it was presented at this conference how you could keep on streaming data even though you change the local oscillator frequency. You can update the software of RTL SDR to do so. And the last thing that we did is we changed the laptop with the Raspberry Pi 4 because it provides a USB 3, which is nicely compatible with the B210. And so because GNU Radio was ported to Raspberry Pi 4, we only need to port UHD and libIO. So all these developments can be found on this build root framework, so the BR2 external extension written by Gwengo avec Meru to port GNU Radio to the Raspberry Pi 4. So that concludes the talk with a successful implementation of a radar system. And if there is any question, all questions are welcome. I will be happy to answer. Thank you for your attention.